Hello again, this is Bruce Wallenberg. This is lecture 14 on control of generation. Essentially, we're going to cover in this lecture the many features of the function called automatic generation control, or AGC. You may have heard an older term called load frequency control, LFC. That term was used up until sometime in the 1970s or so, when IEEE changed the official naming of it to automatic generation control. But LFC sometimes pops up. Same exact function. And the idea is that we need to have some function which does the following. It restores system frequency to 60 in the United States, or 50 if you're in a different part of the world where they use 50 hertz frequency. It restores the system frequency, we can just say to nominal, when it deviates significantly from that frequency. It keeps reallocating generation to keep it at economic dispatch. So, for example, if the load is ramping up, we have to keep the frequency near 60, but we have to keep the generators going up, but we want them to go up so that they're always close to economic dispatch. Economic dispatch is performed as a calculation, let's say on a 1 to 2 minute basis, and so then there needs to be some means to reallocate between those, and we're going to show what that is. We need to keep the interchange. Now this comes up with the topic here. We'll see it over and over again in these lectures. But electric companies have, and I'm just drawing some diagrams down in here. These are what are called, we're going to call these control areas. And control areas are interconnected by transmission lines. So these are the transmission lines here. And power goes back and forth across these between these control areas, but the sum of the flow that's over them. So if I put a circle around this and we put a big sigma above it that says we're going to sum the flows, that sum, if this is all the lines that we're connecting, that would be called the interchange. So the interchange, you could use the term net interchange, is the amount of power entering or leaving the system. So if you have a contract with your neighbor and you're going to sell power to the neighbor, then you have a schedule, meaning a specific megawatt amount over a certain time period, and you don't want load changes and frequency changes to take that schedule away. More specifically, if you have a generator outage, then there's a reallocation of generation amongst the remaining generators, amongst the spinning generators. But you have to maintain that interchange schedule because that's there by contract. So that's a very important thing to remember, that it's there by contract and not just something that you can let drift away. Okay. Last of all, monitor and control generators as they ramp up and down. There has to be a control system that says this generator is coming on. Let's ramp it from wherever it starts at, which is 0. They've just synchronized it, closed the breakers. Now they tell the AGC, ramp this generator up to its minimum power, or maybe even to its max. But so there's a control system that will ramp it, and it has a certain ramp rate. They can't bring it up too fast, and so it controls the generators and monitors them. Okay, so this is the AGC, or the Automatic Generation Control System. Now, when we look at generators, the model is always going to be a turbine. It can be generally a steam turbine. It could be just a very small turbine and a gas turbine, what we call a combustion turbine, or it could be the huge turbines of a large steam generating unit. And then here's the generator, and they're connected by a shaft. And we say that the torque that the turbine exerts, so that let's say it's trying to move the machine that way, and that torque is opposed by the electrical torque that's imposed by the generator. And when these two are equal to each other, the machine does not receive energy. It's not going to be. There's no force on it, no rotating force on it, and it's not going to accelerate up or down. So the important thing is that the frequency of the electrical output here, and we can, you know that this comes out here in a sine wave on each of the phases, and if each phase is 120 degrees different than the other phase, and that frequency is related to how fast this is rotating. So how fast this is rotating determines the frequency. Now, if I put too much load on, then the generator slows down. It slows down. In other words, the electrical torque gets to be greater than the mechanical torque if there's a lot of load on. And we'll just look, for instance, now at one generator. Well, if I have too much load, then it begins to slow down. Something has to tell the steam supply, or if this were a hydro turbine, open up more water from the penstock, or open up more gas from in a combustion turbine to produce more torque. So that would be more steam, more gas, more water, etc., to produce more torque to balance this. So the frequency of the system, remember this is very important, the frequency of the system is an indicator whether or not the load on the system is balanced with the mechanical energy input. So we know that this is balanced when this input energy and this output energy are balanced when the frequency is constant. When the frequency is constant. If the frequency is going down, it says that this guy over here is too large. Frequency is going up higher and higher. It means that I've got too much energy input. Maybe some loads have switched off, some large loads have switched off, and I have to back off on the turbine input. But there's a wonderful signal, if you will, between load and energy. That balance is indicated by the frequency of the system. The nice thing is that indication, that frequency, can be measured virtually everywhere in the system. It will be, I'm going to say, virtually identical. The frequency signal propagates extremely fast through the system. So you can say that we have a signal everywhere in the system that tells us whether load and generation are balanced with each other. That's very important. In the future, when you hook up systems such as, let's say, wind turbines, or you hook up photovoltaic arrays, then the generator is not, there's no rotating element, and the frequency that you see is produced by an oscillator, and in the power electronics that produces the 60 hertz AC. And in that case, there's nothing that says that there's no load energy balance there, and you have to build that in. You have to add that to the system. But in a mechanical rotating system like this, That frequency is our indicator. All right, so the frequency is directly related to the speed. If mechanical equals electrical, then the torque are equal, and there's no change in frequency. So we know right now that electrical load over here is uncontrolled. We cannot. There's a very small sense in which we can control it, but we can only control a very small part of it. Most of the load comes on and switches off by customers. They don't call up the electric company and say, I'm going to turn on these lights or these large motors. They just do it. There are some loads that they do control, and the electric utility does have some what we call demand side management where they can switch loads off, but that's a small amount. The loads are basically uncontrolled, so we must simply control this. This has got to be controlled to meet the load changes and wherever the load wants to go. Here is the overall system. The generation control system is located in a computer system. There are lots and lots of communications. So one of the communications is to measure. There's a measurement on a generator, the generator output. So we measure that. We measure that quite fast, and we bring that in. We measure system frequency somewhere on the high voltage network. We bring in the measurement of system frequency. We measure the tie flows. You can see these little diamonds here, which are representative of measuring power flow on transmission lines. So these are ties, and we measure the tie flows. So that's all coming back in. The generation control system then sends information to the generators. There are some systems, they may still be some in operation today, where they sent raise and lower signals to the turbines. Just be a pulse that says raise, raise, lower, lower, etc. But the more modern system sends an actual set point to the generator, to the turbine generator's control system, and says this is where we want you to go, and it makes its best effort to follow that control signal. And this is how we control. Now, once again, we control the generators, we control the ramping, and we try to get them on economic dispatch. We measure the frequency so we know how close we are to frequency, and we also look at the tie lines. So we're going to develop the overall model for the generation control system based on this diagram. The mathematical analysis, this lecture does not go into every equation. You're going to see that if you follow closely in the book. These are all the terms over here below, but we have the basic function up here, I. You can see is the moment of inertia. That's the rotational moment of inertia of the machine. Alpha is the rotational acceleration, and that's equal to the net torque, which is the difference in mechanical and electrical torque. And the angular momentum, if you will, of the machine is equal to the speed times I. These are just different ways of representing this. So you probably in your early physics courses, you did a lot with linear motion. Force equals mass times acceleration. Well, in this case, we're going to sort of translate all of those formulas into rotational. Now, the net power out is equal to omega times the net torque on the system, and it's equal to the angular momentum times the acceleration. That's as close as we get to an F equals ma kind of equation. Okay, we're going to skip a lot of the math and just talk about a general model. And this is a control system type model, and everything is in terms of perturbations around a static value. So we say that the net perturbations in mechanical and electrical. So the mechanical is plus right here, the electrical is minus, and that goes into a 1 over ms, where in other words it's an integration, and it comes out with the change in frequency. So here is the change in frequency, or delta omega, out here. And here's our equation out here, and we can say that the difference in electrical is equal to m times derivative of delta omega, and then you can work it back through this model. Okay, the model of a load. If the load is made up of a lot of large motors, it turns out that if you change the frequency of the motor, that the electrical actually there's a sensitivity. This is the D factor that tells you how much the frequency of the motor, how much the load on the motor changes with frequency. So we say there's a frequency sensitive amount of load. So we're going to feed that back. We're going to say that there's a non-frequency sensitive load change. That's this one. And then this is the frequency sensitive load change that we bring back. And we can build this model here, which again is ms plus d. So this represents the machines and the loads out there. And so now you can shorten it down to look like this. Generator models. Okay, what about many machines together? And you put together the sum of the equivalent for all the machines and the D for all of the motors out there, and then you have the mechanical coming in for all the machines and the load. We'll assume the single load on the system, and the model looks like this. So again, coming back to as if there's only one mechanical input and one load. Now we're going to say that we have a turbine. And the turbine, and I realize that those of you that are mechanical engineers, this is just an absurdly simplified. But think of it this way, that we have a steam pipe coming in, and up here I have a valve. And I can open and close the valve. And so this is it's producing the torque on the shaft that goes to the generator. And as I open and close this valve, I can change the amount of steam that's allowed into the turbine, and therefore I can control the torque that the turbine is putting out. And so we say there's the delta P valve, and to a very simple degree, this is we call this a first order model. This is called the charging time constant, and that's the model that we use of the prime mover of this turbine. So change in valve, there's the change in mechanical, and eventually you get that out to a change in frequency. Now, I said we had steam. We have a steam valve. I'm going to talk a lot about a governor. We'd like to take and we measure the steam, we measure the speed of the rotating shaft. So here's the shaft, and it's rotating, and we measure and we get omega out here, and we have to have some reference point to say, well, what should the reference be for this particular kind of machine. And let's note again that two-pole machine would be rotating at 3,600 RPM, four-pole at 1,800 RPM. Hydro units rotate at much lower speeds, and in any event, we have a reference for the machine and the measured. Here's the deviation from the speed that we want. Now, regardless of the speed, okay, over here we have a generator, and it still puts out, let's go back to the USA here, it still puts out 60 hertz. No matter what the overall speed is, because of the number of poles, it'll end up being 60 hertz. But we're worrying about now about controlling the speed and the speed going up and down. So we have a speed deviation, and we have a device in here, and I'm just talking about this loop here, which takes that difference, multiplies it by a constant, and integrates it, and changes the sign actually, and it says if it's plus, it opens the valve. If it's negative, it closes the valve. So there has to be a minus sign here that says, okay, if the frequency goes down, if this is below, this is negative, then I want to open the valve, more steam. If this is positive, meaning I'm above the nominal speed, then I'm closing the valve and reducing this. You've all seen pictures of the James Watt steam engine. James Watt invented the first steam engine and used them for pumping water out of mines. And he invented a governor so that he could make it run roughly at the same speed. The governor had these they used to they used to call it the Watt governor, or the fly ball governor. And here's a shaft that's going around like this, and you had weights out here, and the weights were on a slider like this, and so here's the weights, and the faster it rotated, these went out. Let's say there was a spring in here, and they went out. And so if it went fast, they went out, and this went up. And so if it went up too far, then this began to close the valve. If it slowed down, then the spring pushed this back down, and as it slowed down, and it allowed more to come in. So James Watt had a completely mechanical governor. You have a governor on your car, most likely, called cruise control. You put it on cruise control while you're on the super highway, and you set it for, let's say, 65 miles per hour, and the car should try to hold 65 miles an hour. If you come to a hill, you can often hear the engine start to take on more fuel and run a little harder to try to make it go 65 miles an hour up the hill. You come up the hill, and you get to the top of the hill, and now the car begins to speed up because it's no longer going uphill, and the governor detects that, or the cruise control, and it backs off on the engine. It's the same thing. Lawnmowers. At least I used to have a lawnmower that had a governor on it, and as you go into the heavy grass, the motor would slow down a little, and this very simple mechanical governor would speed up and put more gas into the mower to give it more force to cut the heavy grass. And then once you were through the heavy grass, the mower would speed up a little, and then the governor would slow it back down. So you're used to seeing these kind of simple speed controls around you. And generators have governors. Now, what we're going to see is that the governor is there to try to regulate frequency, and it can do a certain amount of that, but it doesn't do everything. We're going to see later on that the speed of the machine and the governor, if this is the power out of the machine and this is the frequency, well, at a certain frequency we're operating at a certain power, and the governor has a characteristic. This is the so-called droop, and what it says is that if the frequency goes down, let's say to here, well, then the governor increases the machine's output. Now, what that means is that it increases it here, and that's it. That's all the governor will do. The governor does not try to force the frequency back to the nominal. Let's say here is the 60 right here, and so the frequency goes down because all the machines are a little heavier loaded as the load comes on, and so when the frequency goes down, it increases the output of the generator. That's exactly what you want. Frequency's going down. I want more power out of the generator. So once the load, if enough power comes out of this generator and other ones like it, to balance things, okay, remember we said that the load and generation balance is measured by the frequency, or is indicated by the frequency. But once the frequency stops dropping, and that balance is restored, we might be operating at a lower frequency. And so then we need another system to come around it to bring the frequency back to 60. We'll come back to that in a minute. But to get this droop, we have another system here, a control system that comes through this gain R. And when you reduce this model down here, this is the governor model here. This is the governor model, and there is a load reference set point that says, well, where do you want me? Do you want me over here? Do you want me at this amount of power at 60, or do you want me back here someplace at that amount of power? And so the load reference can move the characteristic back and forth on the scale here. It can move it, so the line literally moves without changing the slope or the droop. It can move back and forth. That's the load reference. That's the thing that moves it, that says where do you want this to operate. And the frequency changes here. The difference between omega and omega ref is delta omega times 1 over R. That gives us the input here that gives us this change. That gives us, so that tells you where it's going to go just due to frequency changes. So I've got the load reference to set it on this characteristic, and now the frequency changes. So once again, the frequency comes down like that, the generation goes up like that. And if that's now balancing everything, the frequency stops changing, and basically the load and generation are back in balance, except the system is slightly slower. It's going around slightly, the frequency is down, and all the rotation is slightly slower. Now, is this how noticeable? It's fractions of a cycle per second. Fractions. It's very, very small. But large turbine generators are designed to operate at a certain speed. They don't want to be operated too far off. So the control is very, very tight around the nominal speed. So we talked about the frequency and the fact that I could move it back and forth with the load reference. Now here we have two generators, and I have unit 1 over here, which has a steeper slope, and here's one that has a much lower slope. And now the frequency drops. So the frequency drops, and I get this much generation increase on this machine. The same frequency drop. Now, these generators don't have to be on the same bus. They can be quite far away from each other. But do remember that I said that the frequency is a signal that's in the power system, and it's propagated very fast, so that virtually all the machines see the same frequency at the same time. So the frequency goes down at this machine and it goes up by this much. This one sees the same drop in frequency, but due to its slope, boy, we get double or triple the amount of increase on this machine. Well, essentially this would be a larger machine, okay? It's a larger machine than this one. And we would want it to change more, to take on more generation changes than a very small machine. So a steep slope means that the change in frequency is not going to produce as much as this kind of low slope here. But they all participate. They all should participate. All the machines have governors. They have to have governors. They have to have the governor operating, and they all participate in trying to regulate. So again, frequency drop because, let's say, some big amount of load just came on. So now the frequency goes down, the load generation balance is out, and the frequency it's dropping. So the governors start putting more steam or more water or more gas, and eventually they both increase their output. Now the generation load is balanced again, and the frequency is restabilized, but it's restabilized not at F0, but at F prime. Now that's a little bit of a problem. We don't want to sit there and operate at F prime, but at least it doesn't keep going down. So the first, you could say the first means of controlling frequency are the governors on the generators. Now we've got our model now, and we want to show you here is that if you remember, this is the MS plus D is the rotating mass and the load. Here's the delta frequency out here. Here's our prime mover model with a P valve in here. Here's our governor, and we take the delta frequency, multiplied it by 1 over R. That's the droop, D-R-O-O-P. Okay, droop. That's this R constant, and we feed that back, and we get a control signal in here to the governor. So this is the very first model of the power system, and here is our load reference set point. Now, if we change delta omega, and this is the change in load, always have to have this negative sign here. You for the most part you can ignore the D, but this is the overall formula that shows us how the power system, how all the generators are going to respond to a load change. And you take the 1 over R, see the 1 over R1 times delta omega, that's the change on generator 1. 1 over R2 times delta omega is the change on the second generator, all the way up to N generators. So this would be all the generators. And so that's the overall response. You sum the 1 over R's and divide that into delta P, and that tells you how much of a change you're going to get in the frequency when you have a certain amount of load change. Now we're going to model the tie lines. Okay, here we've got our tie line. We've got 1 and we've got 2, and we use this. That should be so familiar now. This is the linear, or we can sometimes call it the DC power flow model, and we say, okay, the tie line is 1 over X here, and 1 over X for the tie times the radian difference here. And it turns out that the delta tie flow is like this, and if we do the proper math here, we say 1 over S times the change in omega is the tie flow. So we've got this change in tie flow here, P tie, right? So there's P tie going across there, and here's a formula for that. Well, now we get to this model. I want to indicate to you that this model appears in Ned Mohan's book on basic power system analysis that's in this series that's on the University of Minnesota's online series. And it appears there. It's also part of the labs for that basic power systems course. I didn't invent this model, and neither did Dr. Mohan, it comes originally from a book by a man named Leon Kirkmeyer, who wrote one of the first sets of books on the power system operations. And AGC was a big part of the book that Leon Kirkmeyer wrote. He was an engineer at General Electric Company in Schenectady, and he came out. It doesn't use always the same notation. He wrote those books of his in the 1950s, so it goes back quite a ways. So I want to cite the fact that Leon Kirkmeyer came up with this model. But here we have two generators. So what this is it's a generator in one power system, a tie line, and another generator. So here's number one up here, and then two down here. So this is number one. Here's number two. Okay, and this represents the tie line. So here's 1 and 2. And we're going to send power back and forth over the tie line. So this is a control system type model. So we have the MS plus D, the prime mover, the governor, the 1 over R1, and then we have a delta for the load in both. So we can have a load that's on each side of the system here, and we have the generator model, the prime mover, the governor for number 2. And depending on the omega 1, here's the omega 1 here and the omega 2, we difference them here, multiply by T, this constant which is related to that 1 over X times 1 over S. We got the tie, and notice that in one system the P tie is plus, in the other system it's minus. So if I define P tie as being this way, well, it's plus to this system, it's minus to that system. Well, if the P tie is actually negative, obviously it's going in the opposite direction. It can flip back and forth. Well, this is a very nice model, and Dr. Mohan in the lab for the basic power systems course built a model of this using Simulink, the MathWorks MATLAB model Simulink. And we use it in the labs for that course, and you can go in and change the load, and you can watch what happens on each side of the tie line and how the generators respond and so forth. And so the frequency response, here I changed the load, so the load goes up like this, it goes up, and the frequency, notice what does the frequency do? The frequency just comes down and it stops moving. Okay, we've remember I said frequency not changing means that I've reestablished load and generation balance again. Now this is with no governor action, but with the governor action it tries to get it back, but I still have this error, and that error is this right here. That's the delta omega. This would be the frequency response if there's no governor action. Well, we don't want that. We don't want that. Now that is simply stabilizing the load change with the D constants, and you don't want that. That's too much. This much frequency change is not a good thing. But if we have the governors in there, it'll control it, but again, it won't bring it back exactly to 60. It gives you this final error. Now, we said that the governors control, and they bring the frequency decline back and slow it down and rebalance the system, but the frequency is not at 60. How do we get it back to 60? How do I get it back to 60? Well, we have what we call a supplementary control, which takes the same delta omega and it brings it out, and it comes back through an integrator here, and it says I'm going to keep adjusting the load reference until this goes to 0, until the delta frequency goes back to 0. That's called a supplementary control. Well, that's the AGC. And it doesn't operate at one power plant, however. It operates as a central entity, and what it does is it has to measure the system frequency and then compare it to 60 hertz. So where do you get a 60 hertz standard? Well, we use a time standard, the NIST in the United States, where the standards are set. There's a cesium clock that puts out a very, very accurate time reference and is transmitted by radio. And you can buy a unit that has an antenna, and then you have a very, very accurate time clock, and then you can watch your own frequency and compare it, by just counting over many, many cycles, how fast it is compared to the cesium clock, and you can tell whether or not you're right at 60 or not. And they built that into the hardware. So basically, you have your own frequency standard in the control center at the power company, and you measure the system frequency. You always want to measure system frequency on a high voltage bus. You don't want to measure it at the wall socket, although you can. But the problem with the wall socket is that if somebody in the basement of your building suddenly throws on a big machine, some big pump or big blower, the phase angle is going to change slightly, and that gives a jump in the frequency. So it's not accurate to measure frequency on in the wall socket as much as you want to measure it out on a high voltage system where phase angle changes will occur, but only when there are big changes on the system, when there's a real change in frequency. Okay, so we're going to show how this overall system is built and how we can build this up. But if you only had one generator, then you could build this right in here, but you have to have a measurement of frequency error from the nominal that you want. Now here are the rules of tie-line control. The rules of tie-line control were built in long before I was born, and they were worked out, and it's a very good system. And so we're going to say that I have a load in area 1, and then I have some generation in area 1, and I have some generation in area 2, and I have some load in area 2. All right. Now, if there's a load change in area 1, what's the frequency going to do? Well, if the load increases, we're going to have a frequency goes down. The frequency will go down. So this says that the load is an increase in area 1, and the frequency goes down everywhere. In other words, omega is everywhere. I'm going to put some big arrows that say that omega is the same both systems. Now, what should I do? What should I do if there's a load change in area 1? I should increase the generation in area 1 only, and the generation in area 2 should not be changed. And so if I increase the load here and then I increase the generation here, I will keep the net interchange schedule. Well, let's come down and say, okay, suppose the load change in area 1 was negative. It went down. Now the frequency is going to go up. Now I should decrease the generation in area 1. If I switch to area 2 and I say, well, let's say there's an increase in load in area 2, but I want you to look at this net interchange signal here before we go any further. Let's come back to this. An increase in the load in area 1, the frequency goes negative everywhere, but the net interchange goes below. It's negative. The delta is negative, meaning it's a little bit lower. So I have a minus for the frequency and a minus for the net interchange. Now that's going to tell us that I need to increase generation in system 1. If the load goes down, then they're both the same, but they're both positive. And again, that tells us do something in area 1. Now, if I change the load in area 2, okay, this is negative, but this one is positive. They're opposite each other now. That tells me that the load change, that the generation 2 should change when these are opposite. If the load change is negative in area 2, well, then this is positive, but this is negative. Then I know. So I can use the frequency change and the net interchange, the change in the net interchange flow, and I know then whether it's area 1 that should take action or area 2. Very, very clever system. Very clever system. Frequency drop, net interchange drops, boom, I know right away that it's P-gen is in area 1 that needs to shift. If they're both positive, again, it's P-gen in area 1, but I need to decrease it. So if you look at those rules for a while, then you can understand that by measuring the tie flow, okay, so I measure the tie flow, and I put that back into the control system, and I measure frequency. Now I can measure the tie flow. I can measure it at either end. It's often done just at one place, and the signal is sent to both of them. But I need to measure the tie flow, and by definition, we all agree the tie flow is considered positive in a certain direction. So then the schedule for me is positive. The schedule for this guy is negative. Okay. So we invent something called area control error, or ACE. And each area has an ACE, and it says that for area 1, it's the deviation in net interchange minus this bias constant B times delta omega. ACE for area 2 is the net interchange for area 2 minus the bias constant here, and these are going to be similar, times delta omega, which is always the same everywhere. So I can say now I'll take the delta frequency and I multiply it by the bias constant, and I'm going to add that to the delta tie line. So here comes my delta tie line signal here, and I add them together, and so this signal right here is ACE. That's the ACE, is right there. And I use ACE, I take the integrated ACE, and that's my control signal in. And that will restore frequency. And you notice again, this is area 1, this is area 2. So these represent different geographical areas. Here's 2, here's 1. And so this is the and they're called control areas. This one is controlling its generation and looking at the tie line and its own frequency. This one is looking at its frequency and its tie line flow, controlling its frequency. And they will achieve the correct change, so that if I have a change in load is one thing. With my students, I always like to take the example of a loss of generation, because that's a big occurrence. And I always say, okay, we've got a 600 megawatt generator, and all of a sudden something goes wrong inside that power plant, and that generator is offline. They have to take it offline, and they open the circuit breakers, and they just take the steam going into the turbine, and they divert it and turn off the boilers, and let the unit just slow down and come to a halt. But as far as the power system is concerned, there's 600 megawatts. Boom, it's gone. The frequency is going to start to go down, and it will. It'll go down fairly rapidly. Well, that large change in frequency, now you can see things like that, events like that. I remember one of the electric companies here in Wisconsin, Iowa, they said that at a certain time in the previous year, there was a large generator had been taken offline suddenly in Florida, and they felt that event in the frequency change in Wisconsin, in Iowa. So that frequency change propagates over the whole eastern interconnection of the United States. It's a long. It's felt far away. Now, if a large generator is dropped in Florida, all of the generators on the eastern end of the United States, governor action takes over, and everybody's generator comes up. So if I have 600, let's say that loss was 600 megawatts, hundreds and hundreds of generators go up a little bit and balance the load generation on the eastern interconnection. The frequency is dropped a little bit, but that's the end of it. It doesn't cause a blackout. The system frequency doesn't start going down. It just, balances it back up again. However, so that takes care of the governor action in here on every generator. Helps to restore or helps to prevent the frequency from going down. We haven't restored it yet. Now, who should restore things? But generally, Florida and it's should have the spinning reserve to bring up other generators in Florida so that they make up for that generator's loss. And that's because the Florida ACE will show that they're the ones that have to bring the generation up in their area due to the loss of that generator. Everybody else will see the frequency change, but they'll also see the net interchange change, and they'll cancel out. And the ACE says, do I need to do anything? If ACE is 0, it says it's not my job. It's not my job. If the ACE is positive, it's one thing. If it's negative, it's another. But if ACE is 0, it says it's not my job. And so this formula is designed to balance out the change in net interchange to the change in frequency. Well, the thing was lost in Florida and all the other surrounding areas. This bias times delta omega times the delta net interchange would balance out, and that would come out 0. So all the rest of the interconnections looking around and saying, it's not us. And eventually Florida would restore by bringing up more generation. That would move the frequency back, and that would move the net interchange back. Okay. Now, if we're going along with the load is going up, let's say it's ramping up. Every once in a while, we have to decide, well, where should the generators go when the AGC says, okay, start moving the generation? And what we do is we remember our old participation factor. It's called the economic participation factor. It's covered in the economic dispatch chapter of the book. And so whatever the change in total, there's a participation factor for each generator, and so we take its base amount times this fraction. This basically says if the total change is so much, how much of that? This is a number from 0 to 1, okay? And it's a fraction of it. It might be like 5% or whatever. 3% of that gets allocated to generator I. So there's a new value, and so this helps track economics by using this participation factor. Okay. Now, there's a generator control loop that says, well, here's my generator out here. Here's the load reference, and the generator output. I'm gonna measure it. So we can put our little diamond up here, and that says I'm measuring the generator output, the P-gen here, and I'm going to bring it back into a control loop to to set it where I want. See, this is the new desired value here. So if I'm sending a desired set point. Now, what we want to make sure you understand is that here's the generating plant here, and here's the control center, which might be hundreds of miles away. And so the telemetry information as to where the set point goes is transmitted to the telemetry station at the power plant. The measurement similarly is brought back, usually on the same communication path, back to the telemetry master at the control center. So this control of the generation is done like this. So there's a thing it's monitoring the output of the generator and trying to bring it to this desired set point. Okay, then we come to our large diagram here, and what I want to show here is raise and lower. Now the generator is out here someplace, and we send either raise lower commands or we send desired generation commands to the generators, and we get this coming back. So this is this is just the AGC control system, but there's a control for the generator units out here. Here's the desired value that it comes up with. Well, notice again we have my penalty factors in here, and we have the base, which comes from the ED. These come from the economic dispatch calculation. And so any deviation in generation is allocated through the penalty factors to give us the desired value of generation. Now, we don't build a control system anymore with analog computers. They used to. They stopped many years ago. This is all done in digital computers, but we wanted you to see the flow of the signals. So we take the deviation in generation, and this is the sum of the base points here. This is where the total should be, so the deviation goes out like this. So I have the desired value for each generator. Notice that I take there's a unit error in here, and I bring that back, and I'm going to add that to the ACE signal. So that the ACE is telling me how much total generation do I want to go up or down. ACE is frequency minus the standard times beta. So here's the bias, the so-called frequency bias constant with a minus sign here, and here's the sum of all the tie flows added up, and here's the scheduled net interchange subtracted off. I take a negative of that, so they're both minus. That gives me ACE. And I take ACE, the only thing I'm doing here is I'm taking the unit error, meaning where should the unit be, and the sum of the unit errors that maybe my units aren't tracking properly, and so I need to keep forcing it to track them. And I integrate that signal, and that's my input to the overall. This is all executed in a digital computer program, and typical cycling time every 2 seconds. It goes through that program and allocates generation. Some of the features that you will see: assist action. So if the economics says that only one generator should be moving and it's moving very slow, we may assist in getting the frequency back quicker by having some of the faster acting generators move until the slower one catches up. Filtering the ACE, this is a very important topic, because the ACE signal goes up and down. And oftentimes, if it goes up, then you say, okay, everybody go up. The generation all has to go up, and the ACE turns around and goes back down. All the generation go down, etc. And we don't want it to be following random noise. We want it to only follow. Well, there's a lot of papers that were written and theoretical developments on how to get the actual changes and get rid of the noise out of that signal. What do you do if there's a telemetry failure? We don't, if suddenly one of the generator measurements is out or the tie line measurements is out, we don't want the AGC to take the wrong action. We want it to keep doing its job, but we don't want it to go off in the wrong direction. So there's a telemetry failure logic and it can tell if the telemetry has failed because the SCADA system will actually know that. And if there's a telemetry failure, then the AGC should not be telling the generators to do things that are wrong. Unit control. Is the unit following the directives of the AGC? Sometimes they don't, due to problems in the power plant, or maybe there's some other thing going on. But we'd like to monitor the output of the generator and say, you know, we've been telling it to raise its output by 10%, and it's not doing it. Take action. Ramping control. We can control how fast the unit goes up and down. We can keep the units again within their rate limits, so that the unit isn't expected to run up and down too quickly to follow frequency changes. And finally, there are various unit control modes. We can say a unit is on manual, meaning that somebody goes over to a screen and a keyboard and types a number in, and that is where the generator goes. Or it can be on base load, meaning this unit just goes to this many megawatts and sits. Typically would be nuclear plants. We run them up to base load and that's it. Some of them are base load and regulating, meaning they can do a little bit of regulating, but they're supposed to come right back to that base load all the time. Then there are the ones that actually regulate frequency and go up and down with the overall load. We note in the book, the third edition of the book, that something about NERC performance standards, the so-called control performance standard here, number 1, says that the AVG over a period of time times the ACE divided by, recognize the B is the tie line bias constant, times delta F, and so this is the average over a period of time, let's say 1 minute. And so we take the ACE divided by minus 10B, and we take the 1 minute average of interconnections frequency error, and we this has to be less than some constant determined by each. That's a control performance standards. CSP2 says the average over 10 minutes of ACE must be less than this L10 number, which is calculated down here. It basically says the RMS of 10-minute average frequency error over a given year, and is the same for all control areas in the interconnection. Now, what these are about is to allow control areas to minimize those standards, minimize the effect on the generation, the effect of movement. So I should have. This is to minimize movement. The real problem is the up and down of the mechanisms by allowing maximum value of ACE. Larger allowed ACE, the less do the generator's unit need to reverse and maneuver, and the less maneuvering up and down of that valve. So you remember we had this steam pipe on a big steam unit, and we have a valve. Now it's not so critical in hydro units. Hydro units can come up and down very fast. Steam units can't. And if you're telling the large steam unit, go up, no, go down, no, come back up, no, go up more, go down, go up, go down. That's great big huge gearing mechanisms and on these huge valves, and they wear out. And for what? That's the point. You know, you let it chase up and down and up and down. What did you accomplish? Well, that's one of the issues of filtering and so forth. And these performance standards help to allow the companies to allow for that, but still get good control. Thank you very much.